All right, let's talk about periodicity. This is elements in the same group. They tend to have the same chemical and physical properties. There's a repeating pattern, which is really where periodicity, that term, comes from. And we can see those trends in the atomic radius, in the ionic radius. We can see them in ionization energies, electronegativity, and melting points. Guys, it is important that you can define all of these terms as we go through them. All right, so let's take a look at melting points. Okay, melting points depend on the structure and on the type of attractive forces holding them together. All right, so we're going to take a look at the melting points, and in particular, those across period 3. Okay. Okay, so if we look at the metal, sodium, magnesium, and aluminum, the melting point here increases, okay, as the number of electrons increase. Okay, and that's due to the charge of the cation as well, being able to attract those valence electrons and hold them in. All right. Silicon in the middle has a macromolecular or giant molecule structure. Okay, very strong bonds because it's that 3D kind of crystalline structure. This has a relatively high melting point. We'll look at a quick graph of the melting points in just a minute. When we take a look at phosphorus, which exists as a P4, S8, and Cl2, these are simple moleculars held together by those intermolecular forces. And these are fairly weak, with chlorine having the lowest melting point due to the small number of electrons, phosphorus being next, and sulfur being kind of in the middle, although there's not a huge difference between their melting points. And then argon, lowest. This is a monatomic molecule. I don't even know if I would call it a molecule because it's just a single atom. Weak forces, low melting point. Okay, I'm going to draw this and just pause the recording for a sec. Alright, so here is the graph melting point, and this is really atomic number. Okay, and you hopefully can see that I've got sodium here, magnesium higher melting point, aluminum should shown just slightly higher but not very much, silicone definitely with the highest with that giant covalent tetrahedral structure. Then I have the phosphorus, sulfur, chlorine being lower, and argon being the lowest. So that gives you an idea of the melting points. Okay, within groups, there are also trends, so group trends. Okay, for the metals, as you go down a group, the melting point decreases. And this is due to the atomic radius really getting larger. And since the distance is so far, the attractive force decreases between, I can't spell force, between the electrons and the nucleus. And those would be the valence electrons. Okay. If we look at group 7, as we go down the group, the melting point actually increases. And this is because these are diatomic molecules. Diatomic molecules with just the London dispersion forces, which are get stronger with larger electron clouds. So the attractive force is the electron cloud. Electron cloud's more polarizable, stronger / more London dispersion forces. All right, let's look at the trends for electronegativity. Electronegativity, let's define it first, is the relative measure of the attraction that an atom has for a pair of electrons. Let's just say for a bonded pair of electrons. Okay. As we go across a period, the electronegativity increases, and this is due to the increased Z effective. The electrons being added to the same energy level. They effectively only see that increased nuclear charge. They get pulled in. Smaller atomic radius has more of an ability to attract other electrons or electrons in a bond between itself and another atom. As we go down a group, the electronegativity tends to decrease, and this is due to the shielding effect. And that's the energy layers being added, shielding the outer electrons from that positive nuclear charge. Okay, if we look at first ionization energy, again, ionization energy is the energy required to remove an electron from a gaseous atom. As they go across a group, first ionization energy is going to increase generally. And again, that's because of the increase the effective electrons being added to the same energy level. Okay, ionization energy going down a group. Decreases, and that's because it's easier because of the shielding effect and the attractive force for the electron being decreased by those energy layers, shielding that nuclear charge from the outside electrons. Now there are some exceptions to the ionization energy, and you should know them. It happens between the first and the second group, and then between, say, like nitrogen and oxygen. And the idea here is in oxygen, 2s, 1, 2, 3, and then the 2p, it's got a fully filled s, okay? Because oxygen is adding this one electron, okay, it's the second electron in an orbital. Because of the repulsive forces between those two electrons, that you see this slight dip between nitrogen and oxygen. And you see a similar dip between, I have a periodic table with me, between whatever's in the second group, which would be beryllium, and then boron. Beryllium is going to have a fully filled S. For boron, we've got to put this, it's the first electron in the next highest energy level, and it's farther away from the nucleus and just easier to remove, so you see this dip in the energy required to remove it. That'll end this, and then we'll start talking about chemical properties in the same group, looking at different reactions and oxides and chlorides.